start yourself. Dear participants, kindly join the session. No? Good evening, sir. Shivpratap, sir. Thank you for joining and thank you for spending your valuable time with our FDP, sir. Thank you, sir. Anche corso mi discusso e dare ansia per facciamo Sir, Vikram sir, good evening, sir.
Good evening, sir. Are you able to hear me, sir?
Yes, sir.
Okay, sir.
That's sir. We are very much happy to see our
Thank you for the invitation, sir.
capital development program by the Department of CSE in NBK, sir.
Yes, sir. Thank you for inviting,
Your
sir.
presence is more valuable to us, sir. More valuable to us, sir. Sir, give me a time of 2 minutes, sir.
Okay, sir. Okay.
Thank you. Ma Ritika?
Yes, sir.
Yeah. Kindly introduce the Dr. Vikram Pudi, sir, Associate Professor, Department of IIIT, IIT Tirupati. Kindly proceed, ma.
Yes, sir. Sure, sir. Good evening, everyone. It's my pleasure to introduce our esteemed resource person for today's first session. Let us welcome Dr. Vikramkumar Pudi, sir, Associate Professor in the Department of Electrical Engineering. Dr. Pudi, sir, holds a PhD from the prestigious Indian Institute of Technology, Madras, one of the finest institutions in the country. Sir also completed his M.Tech and B.Tech from the reputed colleges, showing his strong academic foundation. Sir's academic credential and expertise are truly impressive. Dr. Pudi's sir areas of interest include digital design, cyber security, and cryptography, which are crucial in today's technology-driven world. I'm sure Sir will share valuable insight and expertise with us. We welcome you, sir. We are honored to have you with us here today, sir.
Yes, sir. Thank you, ma Ritika.
Thank you for the introduction. I think light is somewhat dull. Good evening, everyone. As she told, I'm Dr. Vikramkumar Pudi, currently working as an associate professor at IIT Tirupati, Department of Electrical Engineering. I hope you are able to hear me clearly.
Yes, sir. It is audible, sir.
Okay. So let me share my PPT.
Yes, sir.
So are you able to see, sir? Everyone
Yes,
able
sir.
to see
Yes, sir.
the
It is visible, sir. It is visible, sir.
Okay. Visible. Good evening, everyone. Today, as I introduced, I'm Vikramkumar Pudi. Today's talk is about exploring quantum resistant cryptographic algorithm, which will be used in underwater vehicles, autonomous underwater vehicles. If you see, this is my profession. Currently, I'm working as a associate professor to Department of Electrical Engineering, Tirupati. And as everybody knows that IIT Tirupati ECER triple E, we have only electrical engineering. We have a common like electrical engineering subjects. And then when you go for like M.Tech or something, we have specialization. That's why you can see that PhD in electrical engineering department at IIT Madras. Okay, even though I am from background from EC, but I have this is my education qualification. I don't have any industry experience. And 2004, I think I have joined at Narayan Engineering College for BTech. Then after that, I have completed after BTech and as a MS Master of Science at IIT Madras. I have joined. I can't do PhD. I don't have any master's degree. After two places I went, like one place at British Columbia, only like a few 6 months. NTU Singapore, where I stayed like a 3 years. After that, I have joined as assistant professor and at IIT Tirupati. After that, associate, all these things are like tags, but usually we are all like a faculty, or we will call it ourselves like a teachers at our institute. This is my journey. And coming to outline, I want to give a brief introduction about cryptography, like types of cryptography, and then what different types of ciphers and everything. That since it is autonomous underwater vehicles, I want to give you some insights about underwater. If you coming to here, first of all, what is Earth? This is the question. Like why you before first of all, Earth is consist of two places. One is called surface, other one is called water. like a ocean, and then one more thing we call it as land. If you see, 71% is like a ocean, only 29% is like a land. That is the thing about our Earth. Maybe you can say that many other things you have a lot of species, especially if you consider only two parts. One is the land, other one is the ocean. And then in the ocean, if you see that 71% whatever we have, 71% of the ocean, how much actually we have explored? Can any of you guess? You can get some insight. And in the surface, almost like we have explored lot of means lot of terrain, what is living, what it is. We have mapped almost everything. Like Google Earth, you check Google Earth, it has mapped almost everything. What about below the ocean? Okay, underwater. How much, for example, this is my article. Can you guess me how much we have explored till now? As a point of thing. Can any of you can answer? Since nobody is guessing, maybe some numbers like it. So usually we have only like 20%. Even this 20% is like a countries we are able to explore it. Like 80% is unexplored areas are there. And also there is one more question in the moon, how much we have explored. In the moon region, almost like means maps wise, I am telling, we are able to map almost like 80 to 90% of the moon. But whereas in our Earth, in the ocean, we are able to map only 20%, rest are like 80%. Actually, this gives like a lot of scope for so much exploration. And coming to here, why you need autonomous underwater vehicles? You see, one of the main reason we know surface what exactly is there, we can see or we can sense lasers and we can send it. But whereas the underwater, it looks like full of water. It looks like, for example, very, very peaceful kind of thing, water. But when you go for inside something, we don't know what exactly is there. Some places sharks will be there. Some places volcanoes will be there. Some places like a different kind of a terrain and underwater currents. You know that there is something called underwater currents will be there. So you want to explore those areas. First, we have to send some vehicle, underwater vehicle. And that is autonomous is even much better, which you can control from the, you will go to the ship and we will send the autonomous vehicle and this will explore the whatever region, everything will be there. Actually, this is then we can map it into our maps or something. This is actually useful for navigation, ship navigation or submarines and many of the places this is really useful. Like, and all of you don't confuse with an autonomous underwater vehicle with the submarines or something. Autonomous vehicles are the one unmanned kind of thing where we will send without any man or something, then we will capture it. And coming to here, how much actually autonomous vehicle will cost? Like you can see here, micro, like you can usually micros are used for maybe in the small, like you can even do like our projects or something, $500 to $100. That is small AUVs, usually some places where we will go for like up to 50,000 to 250,000. And medium, it will go for like $500,000 to 2 million. Large AUVs means it will go like 2 to 6 million. This I'm telling current, like a RAM of 6,000 or something, it will cost around $6 million or something. Whereas military variants, I think there is a, you can't even tell like how much they are, 1.3 to 1.5 or even more also, we don't know, they don't give the official data. Although they are in the millions range or something. But you see here different autonomous vehicles and their cost. You see that first of all, I gave that what is the length of that 1.6 meters Ramus, which is a, and it will cost from 50,000 to 250, and the maximum depth it can go is 100 meters. You see here Ramus 6,000, it can go maximum ocean depth, it can go up to 6,000 meters. It will cost around 2 million to 6 million. You can see here bluefin, which is like 4.3 meters. And this can go up to 300 meters. You see that underwater autonomous vehicle, the current range is only like a 300 meters to 500 meters, but some specialized one is like a Remo 6 up to 6 kilometers, we can go that. And so what is so difficult? Like for example, autonomous vehicle, we can just send it and then we no need to bother about anything. You see here, usually various purpose we can use like, and first of all, you can look into like a Ramus 100. Autonomous vehicle, there will be some navigation, some battery backup, and there is some circuits, propellers, and the engine. All these things will be there in autonomous vehicles. And this looks very good. Why you need any security or something in this? If we coming to here, there are some incidents that happened. Like for example, Chinese Navy seizure in international waters. There is a US Navy once, and then finally they got like they got their AUV, but they have to go for a lot of dispute or something kind of thing. And Chinese actually they have caught in the international water when that is AUV exploring that. And there is one more thing, how they captured US Navy, I think 2018 or something. And they have captured that when they are exploring the underwater in the sea, ocean, and then they never return like. So basically, when they captured or something, they will try to take data, they will try to steal the technology, they will do like many other things. For example, this is very, very interesting. Like Philippines waters discovery, and they got like a Chinese AUV, and which is like a submarine or something. Actually, it is encrypting data communication links. The main purpose is to collect a intelligence of the kind. So there are two things. If somebody caught our AUV, which is doing exploring, the data should not leak, as well as they're not able. Our technology should not be stolen by other people. We have to be that much careful. I mean, you can see the incidents, 2010 to 2020. Actually, these are only reported ones. Many of these things are happening, but which are not reported outside because of the diplomatic reasons or security reasons. They don't do it. Sorry, I think. So when somebody captured or something, there is one more problem is that they don't capture a they will actually can destroy our thing by using a cyber attacks. So one of them actually these are the security challenge. One is like physical security challenge, like when they captured how they will be security and communication. And as you know, in underwater we don't use any RF signals or anything. We will only use sonar kind of thing. Means sonar in the sense sound waves. Acoustic waves is what we will use like for communications underwater. So that is actually like a limited bandwidth will be there. And one more thing is network and system vulnerabilities, hardware security, and also cost will be there. Somebody captured AUV, I lost like a lot of money kind of thing. And the risk, like we have to see, you see that some of the uh, incidents, like for example, you can take physically capturing. There is one more thing called vulnerabilities. They don't capture, but they will make it our system do some kind of a hacking, and they can destroy the data whatever you are capturing. They will transfer to the other side, and there is a physical capture usually. Almost like $2 million is rushed, and as well as their data, like data also will be export. That is what we have to prevent it. And vulnerabilities such as where we are discussing communication security and physical layer security and navigation security. Data means, for example, we store the data and somebody want to take out the data without our authentication or something, that should not be revealed. There's one more thing called network security. Usually this is like a denial of service attack. We usually have media and firmware. Firmware is entire will be running on some kind of a software firmware, we call it as. That is somebody able to compromise it, that will cause like very, very high risk. So how to prevent these things? So this is the AUV security architecture. If we go there, something called we have layer security and application security. For example, this is the application layer. This is the main layer where we will do data processing, AML algorithm, all the data capturing, sensor fusion, everything will be happening in the application layer. Right? And if somebody can do like they can take data manipulation, all these things, we can prevent these things by using a hardware security, encryption, runtime, like a runtime protection or something can use. One more thing we call it as network layer, like network level connection kind of thing. Here, like a denial of service attack, routing attacks, traffic analysis, like you can do more traffic. So this usually will, to prevent this, you have to do secure routing and traffic encryption or something. Third party, if somebody enters immediately, you have to be able to do. And communication layer. This is the layer where we will be focusing. Like WhatsApp, when you are sending a messages, we will always do like end kind of encryption. End-to-end encryption means basically whatever data I'm transmitting through Wi-Fi, I always encrypt it. Like, and again, what we see is he always wanted to authenticate it. Like, that is called authenticated encryption or something. So he wanted to authenticate physical layer. Like, this is the where real hardware will be. So there will be secure boot hardware side channel attacks is what maybe in the physical layer happens. So our main goal is today is to focus on how to prevent even this kind of a thing. We will focus on avoid using some cryptographic algorithms. First of all, what is a secure communication? For example, Bob is there. You take like, for example, we have given overview of autonomous vehicles. He wanted to communicate with some message with the Alice. She is there far away. For example, in this case, we can say that two vehicles, like underwater vehicle, and whereas main ship, which they want to communicate. Like, I want to send some message or something. I will encrypt it, and then it will become like a cipher text, which they will send to Alice, and then she will do decrypt, and then she will get back the original message. Then comes a person. They to do this one, we need some key kind of thing. This is called security. And there is one more person will come mad in the middle or wherever to fall. This guy goal is always to take out my cipher. And then that some people, if two of them are talking, third person will come always and keep their ear and they will try to learn it. So this is the one he always wanted to get. And then biggest problem about the secure communication, key exchange. How do you exchange a key? That is the biggest problem. And to do this thing, we have to use a key exchange algorithms. Now what happened is, previously key exchange algorithms thinking that we have only that normal conventional computer or normal computers will not able to know this, break this key exchange algorithm. But recently quantum computer came. If quantum computers can go up to 10,000 qubits, none of our computers are safe. They can able to break this key exchange algorithm. They will able to find out what is the key. Once they found the key, then this you can know what they are communicating. So this is the secure communication. And before that, I wanted to give you history about cryptography. And you know that there is a king, like historical, like it was 405 BC or something. So they wanted to communicate or something. What they have done is they have so many surveys or something. In the survey belt, they have like random letters or something like. Greek general, he sent this one to some person and he sent. And when that other person received or something, he has to arrange it. Like, for example, here you have to roll properly, otherwise it will be in a different fashion. When they roll it but wooden pattern or something, and you are in danger, like kind of thing, you go. So then he went to war and then he defeated Persians. Like, so this is one of the ways to hide a message. It's not actually like encryption, but if you know the method, for example, you give like this pattern, how many times if you rotate it, they will be able to get it. And there is one more thing called, for example, here A, B, C, D letters, correct, 26 letters or something, they will arrange like that. A, B, C like that. For example, they are not able to arrange like 26, so they went for I/J kind of thing. So instead of sending a message or something, they have written like A means they will substitute 1 1, B means 1 2 kind of thing, substitution kind of thing. So to this is also they have used. And there is a, for example, this is the one they have used. And there is a one more thing like a crypto analysis. For example, whatever you are sending, cryptography message or something, in Queen, like one of the example is Mary Kunospa sent a coded message to her supporters who are plotting to murder eligible one or something like. So when they send that message, and they have eligible one secret service, they caught that message and then they are able to use the crypto or else they are able to delete it. And then the person who was sent, she got executed for her treason. So the crypto analysis is very, very important to break a cryptography. Our goal is to send a message, even quantum computer cannot break it. So there is a cut file system. This is the one way of hiding a information. Like you see here, this Gopi, Bhagya, Madhu, or this one they have written. Arrange it, these letters or something. For example, this Karpade system is the one which will give you all numbers to the alphabets kind of thing. And when you decode this entire sloka or something, you see this is absolutely equal to pi by 10 or something. So pi is the one of the mystery in the world to get a accurate values for the pi. Many people are struggling, but actually this is hidden in our one of the poems kind of thing. Maybe we'll find so many things like this. They have hidden and then they have propagated as a poem to other people. It's a great intelligence they have had it. And there is one more thing, Voynich manuscript. If you see this Voynich manuscript, there is a guy in the 16th century. He has written in the, if you see 16th century or something, usually doing a research of certain things, thinking beyond what human capable means, what they're told by Bible or maybe some other priesthood teaching is just sin kind of thing. They are not supposed to go beyond their teachings or something. What they are. So what this guy has done is he is wanted to create a wanted to research or something, but he's not a he makes sure that other people they cannot know about that, and he started drawing some paintings about biology and all these plants, and they have started a gibberish kind of thing he gave like, and then nobody cares about this, and he is actually doing his work. Finally, there is a one guy who is a book collector for that very interesting guy. He went to some church or something. They found this book, and then it felt like very interesting. And actually, this online PDF is available. Somebody want to break what actually has written. It's very, very interesting. And the strange thing about he could have used some key or something. He is lost. Because of that, nobody is able to decode this book. They are understand that that guy has done something related to biology or maybe something related to that. But they actually never understand what about this book or something. They're still struggling to find actual meaning of this. Okay, if somebody is very interested in challenge, you can download this Spanish manuscript and then so keys missing kind of cryptography. Correct. Nobody is able to decode it. So that is what we want. Without keys, nobody is able to break it. And there is one more thing. Julius Caesar, he invented a one more cipher. So he will replace the words with like, for example, he moved each rotating kind of thing. So he replaced that A replaced with D, B replaced with E, so on, so like that he went, and he became I came, I saw, I conquered. When see, when D, we see like that. Would have read YL, BL, GL, YL, FL kind of. And this is the one that about that. So what exactly, for example, I have some message which I want to transfer to other side or something, correct? So I will rotate this one. For example, A is 0, correct? We will start from here. 1. Instead of that, let's assume that A is starting from here, D or something. From here, you paint like A, B, C, D kind of thing. And then you can use like a mod. For example, if you want to know certain letter and what is the numbering of that one, you can just use like a mod 26 or something. You will get back that. So you will rotate clockwise or anti-clockwise to shift the letters. When they have done it, shifting of the letters, and this is the secret message or something like this. These are all like secret messages they have created compared to normal message. What is the drawback about CSS cipher is, and for large messages this is useful. You can take like a histogram of the histogram means, for example, you have this some above message, how many times a came. So A came like, you can do like probabilities like 0.08 time or something. You can plot like this frequency analysis of a repeated text. E is the one appear in any of the text. You write like very, very big paragraph or textbook or something. You try to count for a number of times E comes. That is the highest number of times. After followed by T kind of thing. After that A, I, OML like that. Usually if you use a frequency analysis, CSS can be broken. And that's how usually cryptanalysis people, so CSS also failed actually. After they went to very advanced mission, this Enigma mission, no, you can see here, and here these letters are there like A, B, C, you can type, and then it will give you different messages to different time. It will go, for example, A, if I type, it will do like a D kind of thing. It is a Enigma mission. So this was very, very powerful mission. Like until World War II, there is a guy, like maybe any of you have watched, there's something called Imitation Game. There's something called Imitation Game. That guy is able to break this code. Like for example, if you see inside this very, very complicated system, here you can see that wire. For example, E is actually, if you go and see that wire, he is replaced with Z. For example, so it's called shuffling kind of thing. When I pressed E or something, it will go like this, all the mechanism. It will give like a Y kind of letter. So these are very somewhat complex mechanism where, for example, if I press like kind of T, then it will go to the shuffling of the numbers alphabets, and it will go to all the rotors. One direction it will go, and it will come back in one direction, and it will display it different. If you want to break it, this will be like a very, very huge, where I think two something different which can compute automatically. Finally, is not able to break it, but they got some idea. Whenever they are sitting in Germany, they are always giving something called all hail Hitler or something. So that message is constant every time. Irrespective of whatever it is, always they will give all hail Hitler. That is what they take that message, they are able to reverse solve it, and they have got the key combinations here. Like what are the key combinations they are able to get? So that's why they are able to make the Enigma mission. And then World War II, it was a great discovery. So later, people thought if these things are breaking like left, for example, nobody can break this, and somebody thought we are not able to break it. And we have developed some mathematics, some kind of cryptography code, and we thought we are nobody is able to break up. It's kind of a frog living in the well thinks that this is one kind of thing. So what they have done is, let's create some cryptographic algorithm or ciphers. We'll give to public. Since everybody can know this algorithms. And if nobody is able to break in the world, then that will become like a secure kind of thing. And in that one, they came something called modular arithmetic. So modular arithmetic means is kind of a limiting the number of like a number of, for example, For example, you take like our clock or something. Usually we'll have 24 hours, but we have only limited from 0 to 11 kind of thing. So this is called mod 12 modular arithmetic. Find out what is the advantage of this. Number of occurrences. For example, number of countable kind of. This is called finite field or something kind of. It's not having a unlimited numbers. For example, 0 to 11 is there for in our hours clock or something. For example, 22, we just do like a mod 12. 22 mod 12, if you do, you will get back like almost like a 10 hours or something like that. And similarly, this also ABCD, correct? We are naming from 0 to 25. It's called mod 26 system. Model. They found the advantage of model arithmetic is you can hide the message as well as you can recover it if you know the. For example, I sent like a 20 to 10 kind of thing, 10 hours or something. I send it. That can be either 10 a.m. or 10 p.m. If you know that this is a model. And also they have some properties like 5 class 5 model. You can see that model science. This is the actually basic methods they're using in without knowing this. Maybe you can know this cipher, but had this. This is the fundamental. Yeah. So A is like a A is equals to B C. So it will actually exactly equal to B plus D model kind of. It's always simple. Like similarly, multiplication. But one of the interesting properties is P. And if for P minus 1, you take it, mod P equals to 1. This is the one of the Fermat's little theorem or something there they will use. This is the one of the things they have used in the public key cryptography, RSA, digital signature, the cases they are using. And these are the some of the modular. You take any number, example, you can take 7 for mod 18 to 7. Equal to 1. The sequence is repeating periodically. Periodic sequence. You can see here 5, 12, 8, 1. It is also periodic sequence. Again, the sequence will repeat for powers of that will create a periodic sequence that actually created a or maybe any messages somebody. Are you able to hear me? Hello, sir. Hello. All of you able to hear me, sir?
Yes, sir. You are able. We are able to hear you, sir.
Okay. Some message. So
the
this is
going fine, sir.
Okay, this is like a periodic. For example, you take any number, any mod or something, you take it, powers you go as a students are there. You can just go and do it. It will always be periodic sequence. Some modular arithmetic. I am just giving some students inside. Usually, it's not required. You write a table or something. For example, you take and then you do that some modular arithmetic for your practice or something. Write quotient and remainder. In general, see, all of you know about multiplication, correct? It's called a repeated addition, correct? Multiplication means repeated addition. But if I ask a division, the people will immediately will tell like a repeated subtraction. Correct or not? Usually will say repeated subtraction is something called we say division, but actually that is the wrong. It's called the representation of a number. For example, 7 by 3 is there. You want to represent a 7 in terms of a 3. That is what 2 into. Maybe you can take. Sorry. For it's called a for a similarly 9 by 10. Correct. Usually we'll write like it. You want to get 2 into 9. 7 into 1. Okay. So basically, it's kind of representing this one 19 in terms of 2 or something. We always feel that quotient is very important. Remainder is not that much important. Actually, you check Chinese remainder theorem or something. Reminders are the quotients. So entire cryptography, the reminders works on the reminders, not on the quotients. Okay, quotients we don't care much. We only care about the reminders. So entire majority of the cryptography works on the quotients. That's what you have to remember. So oh, this is the one of the main mathematics behind this. Actually, this modular arithmetic, we have to study about finite field and a finite field over the polynomial, over the binary prime field, and ring. All these things you have to read in the cryptography. So then you will understand. And then I'm going to give you something about advanced encryption standard. It's called AES, and you go and check what kind of encryption mechanism, or for example, WhatsApp, what kind of encryption is using AES. And currently we are using a Zoom. What kind of encryption it is using to communicate it is Zoom AES. You can go like whatever you go, like any encryption may 99% of the times or 95% of the times we are using advanced encryption standard AES. What happened is this history. I want to let me give you some brief history. This is actually like a algorithm. Previously, people are using DAES, like a data encryption standard, which is invented by IBM. After IBM, they thought that is very secure. But what happened? People able to break. Break means, for example, I'm sending a plain text. It will come as 128-bit ciphertext, correct? Yeah, ciphertext. And then they are able to know what is that ciphertext by breaking. Means they will get the key, and then they are able to decrypt the message. Like now, since they found out that rather than one guy to develop thing. So, because of this, IBM is developed something very good. Let's use rather than that what they have asked. They have given a competition through the submit for encryption standard. They will take the submission. The submission has to do some kind of a checks or something. So IBM has submitted. Many people have submitted like that. So why is it breaking? Let me change my. Hello, are you able to hear me now? Hello?
Yes, sir. It's audible, sir.
Somebody is telling that voice is breaking, that's why.
But previously it is breaking, sir. Now it's okay.
Okay, now I changed over more. If it is breaking, please let me know.
Okay.
Maybe this Bluetooth has some issues, I don't know. So this is one of the key algorithms. So everybody submitted, and everybody thought since some companies submitted, they are very strong. Everybody thought it will get selected. But what happened? Some academician who submitted this AES algorithm means that got selected. So this is a wonderful about our academics. So now onward, that time onwards, if they want to select any cryptographic algorithm or anything, they are conducting a competition. And the competition they are taking and they are making a standard kind of thing. So that is how it is happening. So usually this is a 128-bit plain text I will send to the round 12. and then it will be ciphertext will become ciphertext. I will give to here, and again I will get back my original data. So AES usually, if somebody is using a Python code, just using crypto libraries, they can get usually AES kind of thing. So it actually contains some round kind of thing. You see that round 1, round 2, all these things. Add round key is nothing but a XOR operation. This is, I'm not telling you entire you will learn. I wanted to show you that how basic cryptography algorithm works kind of thing. It is not about, it is very difficult to teach in 1 hour. It takes like 2 to 3 classes or 5 classes. So if you take any encryption standard or something, generally we have something called substitute. You take some A, B, you substitute with like a Z, X, or kind of thing. And then after substituting, this is common, they will shift rows like a confusion kind of thing. Confusion and then diffusion, shifting row kind of thing. They will shift it to, again to confuse, and then they will do like mixed columns again to do the confusion and diffusion kind of thing, so that people will feel very difficult about getting back. And finally, they will add round key. Round key operation is nothing but a XOR operation. You take each bit, 1 bit, and then you will XOR operation with the round key kind of thing. When you want to do this one, it is like inverse shift rows. Like you will come from here to here, and the inverse substitute bytes, and add round key, inverse mixed columns kind of thing. So this is the process. And this is the one usually like somebody want to implement in hardware or something. So you can take plain row and all these things you can go. Finally, how many rows? So let me explain that. Even the quantum computer, they are not able to break advanced encryption standard if they increases number of rounds. For example, here I have that 10 rounds for 128. I can go like some 30 rounds, 36 rounds. If I increase the number of rounds or something, even quantum computers cannot break it. Like you actually, this is very safe to use whichever company. Either you can use in underwater or you can use in normal any of the systems. Even the quantum computers cannot break it, and as well as the data which you are storing in your hard drive or something, you can encrypt using the AES. Okay. So this is the one, like they for substitution, they will take one and they will go through S box and they will substitute it again. Similarly, shifting rows is nothing but according to that, they will rotate kind of thing. Shifting rows here means rotating kind of thing. Operation hard mixed column means they will use this kind of a XOR operation or something. They will do this shifting of this one. So finally, key is there because they are not using each round. They will use key expansion operation. They will key is the, for example, I have 128-bit key. They will arrange like this W0, W1, W2 like this, and then they will do like G is some operation kind of thing, and they will send it to like different phases or something kind of thing. Finally, that's how they will get all the round keys or something. So this is a one which we are using in entire our communications. Now coming to this, you cannot use directly this AES, this called block ciphers on the images or something called text or something. For example, this called electronic code book, as it is plain text they will get, ciphertext they will get plain text, ciphertext they will get, and they will use a key kind of thing, correct? And then let's take this image, this penguin image or something. You try to encrypt it by applying AES. Actually, this leaks a shape of a image or something. So what people found out that since this, for example, say one text is coming, for example, the same data, same ciphertext is coming, good. Same, you give input, same output is coming for the same key kind of thing. So they have invented different modes of, for what we want actually is kind of a random kind of thing. So what they have done, different modes of operation in the block ciphers, we call it as like a CBC mode. For example, they will take initialization vector here. First round, you can take anything, maybe count or timestamp or anything. And whatever ciphertext, this will become for the next one, initialization vector. This will become initialization because very difficult to predict this ciphertext. And there's one more thing called output feedback. For example, whatever is coming here, that they have taken. Different modes are there. One more thing is counter mode. And counter mode means instead of
ciphertext or something, we will use like a nouns plus count, nouns plus count, nouns plus count, like that we will use. That is called counter mode. Whichever it is suitable for our application, we'll use it like. So these modes and everything are available in Python. Like. And coming to this is called block ciphers. Block ciphers disadvantage is it consumes a lot of area. And there is something called stream cipher. This is very, very interesting. And all of you know about XOR operation, correct? The XOR operation, very, very interesting. You take A and you do XOR operation with some K or something. And again you do XOR operation this with K. What is the value, can you guess? This will become A kind of thing. This is the same principle they have used. I have getting my plain text M. This is going to key stream K. They are doing key stream each bit, and they are taking message bit, and XOR operation they are doing, and they transmit to other side. Other side also they will do remove. They will use the key stream, and then they are doing XOR operation. Then I will get back my original operation. This is the called stream ciphers. The advantage of this stream cipher is it actually consumes very, very low area. It is usually very safe, like even it is not easy. It is not very difficult to implement in hardware. You know that we are communicating audio, correct? Our audio. We are communicating audio. Like we are talking like from my mobile, for example, I have my mobile phone, correct? My mobile phone too, I am going to other place or something kind of thing. That is the I don't know, somebody, Madhukumar, he is drawing something. Okay, this is actually using in our mobile phone audio communication. Like for example, we want to encrypt it like each bit whenever we are transmitting, they are using a stream cipher. You see that inside stream cipher, what is happening since it is a FDP. This very, very, very simple. Like for example, many methods are there. They are using like a LFSR, like a linear feedback shift register and non-linear feedback shift register. Basically, this is a linear feedback shift register. Non-linear means we cannot get back. For example, linear means if you know this sequence, you can know that what is the previous sequence, what is the next sequence. We know that one. Non-linear means we cannot know what exactly the previous sequence. Only that we can get next sequence. So these are linear feedback shift register they are using, and by combination of non-linear feedback shift registers and linear feedback shifter, some function or something. It's called grain cipher. You can look into that. Very, very simple. Okay. Hardware implementation is very simple and straightforward. Some of you want to use for hardware implementation, any of the protocols, you can use it. And this is the function kind of GFX or something kind of thing. This is not, don't worry about this X power 17 means LFSR will have named 0 to, what is the size? Maybe if you, 120 or something. This each position is all nothing but XOR operations, nothing but. This X17, X power 100 means AND operations kind of thing. So here X17th means that's 0 means 17th position of element, LFSR element. Okay. NFSR means similarly like this. So this is the one they were using like a stream ciphers. So there are a list of many stream ciphers we have. Among them is like a RC4, cha, salsa, and all these gray. And these are not a quantum proof. Okay, these stream ciphers actually can be broken by the quantum algorithms. So we want to use quantum safe or something, better to use the AES kind of thing. And there is one more problem. We are encrypting a data. Let's say, for example, from this PC to here, I'm transmitting a data. There's one more guy sitting, some evil guy or something. He's sitting. What he will do is, he don't listen our data, and also he will tamper our data. He will tamper here, whatever data I'm getting from here, he will tamper that data. And the why he will tamper is so that this guy will receive some different message, not the original message. And how do you find out how this guy has been done. There is one more mathematical term for this is called hash function. Actually, hash functions are nothing but a one-way functions. It's kind of a fingerprint or message digest kind of thing. So what they will do is they will take huge data or something like 2 power 32 bits data or something they will convert it into 128 or 256 bits. That is called a hash function. They are one-way mathematical functions. So this is how usually you will use for a hash for checking somebody like it. And there are a few of the ones. One is called MD5 output 128 SHA-1. Coming to SHA-1, actually what happened? People are able to break this one. Break in the sense they are able to get back. For example, you are transmitting a message or something. What hash that is able to create, they are able to break it. And similarly, to replace that, they got it like a SHA-2 kind of thing. There's one more algorithm called SHA-3. Actually, what happened? SHA-2, there are no real attacks on SHA-2. They thought that it will be attacked by somebody. So they have created a SHA-3 algorithm. And then, so how this will work is the maximum message size is 2 power 64 bits. Can any of you guess what is the 2 power 64 bit message? It's very, very huge kind of thing. And then it will generate a hash 256 bits according to our needs. So I will take any message. The message is converted into 512 blocks or 512 blocks. And then to get a length or something, we have done like length padding or something. Each block size is like 512 bits or according to the, sometime it will be 1024 or something kind of thing. So when you have message bit 512 or 1024 bit, it will go to this round function, round 0. Like this 64 rounds, it will go through that. 512 block takes, and then it will go to 63 rounds or 64 rounds. And then like that entire message they will do, and then it that finally will generate 256 bit hash or 512 bit hash according to our rate. This is a round function. Round function is nothing but simple additions kind of thing. So this is a SHA-2. In general, we are using this is for many of our applications. For example, I am downloading a software from unknown source or some known source or something. But the guy, whichever channel I'm using that one, that guy will provide a wrong software or something. To identify it, what people have done, they will provide along with the software, they will provide a hash code or something. You just run some commands on hash, you know that your hash key. So you can match both of these things. Okay. And similarly, and also this is useful. For example, some people will use torrents or something to download some software or something. Correct. Sometimes we don't know what is that actual software. So you go to real software guy. That guy will provide some hash code I can. So when you run this entire software or something, you will get hash code, and then you match both the hash things. And similarly, actually, they found out that SHA-2 can also be broken away in the future sometime. They again conducted one more competition, SHA-3, I think. 2007 they have started, 2012 they have finalized. That one is called Kechek. So you can see that 2007 to 2012, you know how many years they have been. It's almost like 6 years. That guy has to prove that their algorithm is good. So many comments will be coming. So finally, this is not going to very technical details. So basically, it's kind of a sponge construction. What is means by sponge means, usually what our message means, it will go to the sponge kind of thing. It will go from here to here kind of a sponge kind of thing. And this is called squeezy kind of thing. So once the message got observed, this is called observed, then they will squeeze it to number of bits. That is called sponge construction. Based on that, they have created this kind of a SHA-3 algorithm. Now what they are telling, for you want to use for quantum resistance or something, quantum resistance algorithm or something, they are telling to use it SHA-3 algorithm, not the SHA-2 algorithm. So if you are writing any proposal or any other thing, try to use it like a SHA-3 algorithms. So this is all good. Like for example, how do you, this is, I think mathematics is not required. So what people will do is they will use like a encryption plus hash algorithm. They create something called a tag kind of thing, hash. Okay. This is the one is what they will be transmitted to the other side kind of thing, other guy. So this is the hardware like message authentication code or something called. So first you find out a message authentication code, this MAC tag. They found out that this you can do many ways. Usually our hardware security modules or authenticated encryption modules always use this kind of a mechanism. So plain text, then you found a having hashtag, and then you can do symmetric key encryption, block cipher or stream cipher you can use. You will get a cipher text, you transmit to other server. And then you have a key kind of thing will be there. That key is what usually people will use for to get back original message. This is the one. Usually there are no practical attacks are there. And what happened is, these are all actually like it consumes like a lot of area or something. Let's assume that you want to build some security protocol for something called autonomous vehicle or underwater autonomous vehicle or any other thing is fine. And how do you build the security protocol? You know about basics, correct? Whenever I want to build or anything, first thing is confidentiality of transmitted data or encryption of, you should encrypt the transmitted data. That is the first, that is called security. Second one is called message integrity. For example, whatever data I'm transmitting, this guy is transmitting from here to here. Some guy is able to transfer it. Okay, in general, how data is transferred from here to here, it will go to some server or something. From the server to again, it will go to some other place, user kind of thing, where some attackers, they will modify data and they will transmit. So for one of the examples here is like this. Let's say one doctor is wanted to monitor patient health by using a remote means. So the remote guy will have some kind of heartbeat monitor, some ECG monitor, some EEG monitor, some monitors, they all have it. So whenever that ECG or EEG data goes to the collected from a patient, it actually go to some kind of a database or something. From there, the doctor will receive that data. Imagine that guy is going to, the pulse is been decreasing or something. This some guy wanted to tamper a data. He tampered a data and he sent a wrong data to doctor or something. Then the patient will die kind of thing because of this wrong thing. So if somebody is changing or something, data, it should able to data, that is called message integrity. And all these things to work, we need to have secret key kind of thing. If we don't have any proper key exchange mechanism, we are dead kind of thing. So what happened is, this quantum computers, this key, whatever we are exchanging, algorithms, they're called asymmetric key encryption kind of thing. That quantum computers is able to break this key so that we can get a key kind of thing. So asymmetric encryption usually used in many places, applications like banking, finance, and data signatures, many places. And other one is called, let's say we have created a very great algorithm or something, but that is not efficiency, means with my reasonable amount of money, reasonable amount of resources, if I am not able to implement it, that protocol is completely waste kind of thing. So it should be reasonable. So that's why, actually this is one of the project where I did in a postdoc, and we have this prototype also. We wanted to do like some trans security for the ATMS, means automatic traffic monitoring system, or like you can use like a monitoring system, automatic monitoring system. We want to monitor data and by encrypting. For example, these are the models which we are using. One is called key generation, tag encrypt. Tag means it's a basically Akan is a new standards kind of thing. What people have done is this whatever you are using AES followed by SHA, that consumes a lot of area. Why can't we design some lightweight encryption algorithms which will take like very, very low area, very easy to implement kind of thing. So that is Akan is one of the authenticated encryption model. So we will have key generation model, encryption and decryption models, and authentication kind of thing. What is authenticated encryption? And there is one more interesting concept which people are using. Key generation is not an easy thing. We are struggling to do the key generation. There is one more concept, it's called physically unclonable function. Physically unclonable function means you in a die where we'll make two ICs, you see functionally they are equal, but you go and see in a structural manner or in different manner, they are not equal, like a noise level or something. There is a guy at MIT, he got this concept like him. And then he created something called physically unclonable function concept. By using that, they are able to create a chip different keys kind of thing. So this is one of the thing is called ring oscillator pop for key generation. So you see that entire this is the above circuit, and this is the below circuit, and the same count and everything. Usually, logically, they should be equal. Logically, they should be equal, but because this ring oscillator, what will happen? The delay will be, we have to place such that the delay should be highlighted. Like because of the delay, whatever ring oscillator generate this time period and this time period of this one is completely different. Because of that, you will get a different sequence. Like it counter one will have different counts, counter two will have different counts. By using that, they will, right? This is called a ring oscillator puff. So this is what we have used in our one of my protocols to we see why I have used is my target is very lightweight. If I use like a PQC means asymmetric key encryption or something, that area requirement will be very huge. It is not easy, which we will see later. And that's why you want lightweight. So here physically unclonable function, you see that this is the entire block diagram of my architecture. You see here, the first step is key generation. And then IV and EID associated data, they are very easy. And then I will take the image and then I will encrypt it, and as well as I will get a tag. I will transmit to other side. And other side will receive the encrypted data and then the secret key and everything. So my device will have physical unclonable function, but in the server we have channel kind of thing where I have to need to store the keys. And I will decrypt the image and then I will authenticate it in the sound system. This is how, if somebody want to do like, it doesn't matter, autonomous underwater or anything, these are the components is required for you in a hardware point of view. Okay, so you have to verify this one. And then you know that when you, whichever you implemented, we have to show it in some demo. We have implemented in FPGA, and we have, and also there is one more interesting. Let's see, images are there, encrypted original. This is the histogram kind of thing. Original image encrypted. And let's say I have flipped one bit in the key or something. You will never get back the original image. You will get back some kind of even decrypted something kind of it. Okay, histogram. So this is the advantage of using this cryptographic algorithm. And this is the demo which I have at here at IIT-Tirupati. If you are somebody coming, you let me know 1 or 2 days before you want to see this demo, we will arrange for you. It's called original image. This is a encrypted and this is decrypted. This is the FPGA board and then OV7670, 30 frames per second it is capturing. And this is actually you want to publish a paper or something. Usually we'll synthesize it and we show it. This is only for how to publish a paper or something. I'm interested, you can use it. And then we'll use like some nice statement like it requires less area, less this much. See, that's why usually we'll do protocol. So coming to here, this is all like you see that all these algorithms require a key. For example, Malaysia, all these things you see, correct? This required a key. But how do you exchange a key without knowing the Eve? That is the question. That is where comes the asymmetric key cryptography. And that is where the quantum computer poses a threat or something kind of thing. You know that our OTPs are also, whichever we receive, they are asymmetric key encryption, correct? OTPs, whenever you log into that, nowadays we are using a huge asymmetric key encryption. So this, how do you do? There is one guy, he gave solution to this that is called Diffie-Hellman algorithms. Excuse me, are you able to hear everyone? Just message me if you are not able to hear me. Okay. This is the algorithm which people are using for the key exchange algorithm. So very, very simple. It's not like very, very difficult. And like they usually let's assume that I have a two A and B people are there. Bob is there, Alice is there, and they have chosen like P equal to 9, N equal to that public key or something. For example, I have this called P equal to 9, N equal to 23 called public key kind of thing. Everybody can know, no problem. And I have a secret key which is like a 4 kind of thing. Alice has secret key 2. So what I will do is, I will take this 9 power 4 mod 23 I will calculate, which is like a 6. And 9 power 2 with 9 will do mod 20, which is a 12 or something. And so what I will do, I don't transmit like what is my secret key to Bob, or Bob won't transmit. Whatever this mod you will get, you will transmit to this side. So I receive 12, I receive 6. And then what I will do is 12 power 4. What is a 12? This guy said something called 12, and I have my secret key 12 power 4. And what is this term? 6 power 4 and mod 13. So this 13 is what will become like a secret, shared secret key or something between them. This is called Diffie-Hellman key exchange algorithm. Can you know that what is the principle behind this? Modular arithmetic. But what happened, Diffie-Hellman key exchange algorithm can be broken easily if the this n size is very small or something. So you have to choose very, very large kind of n or something kind of thing. Similarly, p also we have to choose some kind of reasonable large number. Similarly, secret key also how to choose large. And also, by the way, 9 power 4 mod 23, to calculate this 9 power 4 mod 23, we have different, but it consumes a lot of area. To avoid these things, people have come up with something elliptic curves. And now elliptic curves also they are using nowadays. If you are using key exchange algorithm, means easy elliptic curve Diffie-Hellman key exchange algorithm. But I'm not explaining that. That also I got broken kind of. Broken in the sense quantum computer can break that also. What option we have? Like people have taught. So this is basically this key exchange using like many of our EPN and WhatsApp, Apple, many of the places. What other option we have? So this key generation is what till now we are using ECDSA and all these things. So how exactly we do these things? So and moreover this G power X or something will go like some space or something. This you can read it, will get. But existing algorithm Diffie-Hellman key exchange RSA elliptic curve cryptography, usually normal computer takes 5 to 20 years. But quantum computer, which has given to Shor's algorithm, it can break within days if we have 10,000 qubits. Even if you go like a 10,000 or 1,000 qubits, many of our banking system, our security, our defense, they are in the threat. That's why everybody wanted to go for post-quantum cryptography. So what they have done, NIST has conducted a competition again after 6 to, I think this competition started when I'm doing postdoc. Recently, they have finalized some algorithms. Like last year, this year, they are finalizing some algorithms for this. And you can go for it, announce 6 years like rigorous. So public key and key establishment algorithms. One of them is Kyber kind of thing. So it is based on a lattice structures. No need to worry about what is a lattice. Don't bother about that. I will explain in very, very simple manner. The key concept here is very, very simple. Matrix multiplication. Here matrix means A is not a square kind of thing. S also similar. It's kind of a rectangle kind. AS will multiply and then you will get B values. Let me ask you something. Let's say I gave you A. Sorry. I gave you B. If we ask you to find S, is it easy or is it difficult? Usually what people will say, this is not that much difficult. Usually that is easy only by using some Gaussian elimination method. Okay, you can use a Gaussian elimination method, you can solve. But now this is the so AS plus A into S multiplication, they have done something called error matrix. E kind of AS plus E, and then you want to solve it. For example, let's say I gave you A, I gave you E, I gave you B. If I ask you to find out S, it takes like exponential time. Sometimes it will take, even quantum computers, it takes like a years of the time, provided A size is like very, very huge kind of thing. So that is the advantage of this. That is the one of the fundamental principle how this Kyber post-quantum cryptography algorithms are working. Like this is called error introduction, and it became a finalized. So you see that problem statement. And they have many things like key exchange and digital signature. DLTM is the based on the lattice only. They are in digital signature, which we can discuss tomorrow. We have some time. And then there is a usually it works on something called NTT. All these things like it. The biggest difficulty about this Kyber is hardware implementation. It is not easy. Even if you work for 6 months, you cannot able to implement. It takes like a lot of time to implement in hardware. So what exactly Kyber algorithm is done in 2 steps. One is called, there are 2 schemes are there. You can use like a secure scheme, like a chosen plain text or adaptive chosen plain text. Among them, you can choose one of the schemes. And then attackers also you can resistance. According to your application requirement, you can choose which scheme you wanted. So this is the one kind of thing. For example, Alice, what she will do is she will take some public key kind of thing, private key kind of thing, AS plus E, she will compute this one. And then what it will give is it will give public key A and PK to the Bob kind. This SK is the secret key, E is the error, RD is like a random polynomial. So it can generate Alice public key and secret key. Bob will take this public key and then he has some message. So what he will do is he will do these operations like AR plus E1, PK plus E1 plus message. With this public key he will do, and this anyway A is known to us or something. We will give that A also, which Alice don't know is this R kind of thing. R is like some random kind of thing. No need to worry about it. It will give ciphertext. So E is what we will get access to this ciphertext. We will not get access to some message. So this ciphertext is transmitted to key description. This mathematically looks somewhat, even I didn't go to mathematics. Don't worry about this mathematics. If you do this operation, V minus whatever secret key Alice has, if you do transpose and multiply with the U kind of thing, we will get back our original message. This is the way of transmitting it. This message itself will become like a secret key between us kind of thing. Once you have a secret key, we can use a symmetric key encryption algorithms to do encryption of data. So this is a message, whatever it is like a secret, it will become like a secret key between the 2 people. Like. And you see here, previously we have seen like 128 bits or something, correct? Here the sizes are like 800 bytes, like public key size is 800 bytes. Secret key size is 1632 bytes kind of thing. Kyber 512 algorithm. Even if you do like a very fast computer or something like, it will take like a 0.48 milliseconds or something like that. This is very, very high speed computers, which we have done. Okay. So public key and the secret key. These I just this imagine you want to implement in a hardware parallel algorithm, it consumes like a lot of area. So this is message proof you don't need, and this is the key block diagram. For example, we have random number generator and public key and secret keys will generate, and when we will give this public key to this person, secret key will give to decapsulation size. And then this is the entire like number theoretic transform is what they will use for all this pseudo random number and all these things. We'll use like a SHA-3 algorithms. Many of them are using SHA-3 or SHA-2 algorithms for the pseudo random number generator. This is the overall block diagram. And I think we have explained about this error matrix. And this is the entity. Like for example, what we found is all the places entity is the main thing. For example, entity is number, but number theoretic transform, which is similar to the fast Fourier transform. For example, you want to do, let's assume that I have some A, I want to do convolution of something called B, correct, in a time domain. So what people will do, they have apply a entity here. Similarly, they have apply entity here, and then they will multiply, and then they will find out inverse entity, and they will get back the original image kind of thing. This kind of they will do in a frequency domain kind of thing. So similarly, entity is doing the same thing. We want to multiply A and Sk, which the sizes are like I told you, the sizes are very, very huge kind of thing, bytes, 700 or 1000 bytes kind of thing. You want to multiply it, consumes lot of time and lot of area. So people went with the entity kind of thing, number theoretic transform. Okay, number theoretic transform. And finally, you take number. So this is how we found that working on entity is like good. So it is like a generalization of a DFT, but it uses like a multiplication, like polynomial multiplication. This is the formulas. Like don't worry about this. This looks scaring only, but if you go start working like 1 or 2 months or 6 months, you will know that these things very easily. And whatever operation W we are doing, we use a G power K modern or something kind of thing. And this is the one, what we found is, this is the entity architecture or something, correct? Number theoretic transform. This is the operations. But imagine like a 256 point entity, like a point entity is what Kyber uses. So we went and for publication purpose, I'm telling, we took some simple model, and then this is the usual 16 point itself is implementation. Imagine to do in hardware like 257, it consumes like a lot of area. So we went and proposed something called systolic array based one. Like usually we have taken a processing element of these things, and then we started repeatedly using a less number of multiplications. So this is the one got accepted in the conference paper. I'm just telling, sometimes it is impossible to work on entire problem. You work on small things, try to come up with some new kind of thing. So to compare it, usually you can do that comparisons to get a paper accepted. That's all. Okay. If that area is less, there is no point of publishing. So this is the algorithm. Sorry. This is the algorithm, like number theoretic. This is the Kyber algorithm, which we are working on this. So this is the algorithm. Like these sizes, we have only done up to like for an entity only. In the future, we will do everything in implementing hardware, like key encapsulation, decryption. Maybe it will take 2 to 3 months to implement everything in the hardware. So we are going through this. With this, this is the one. If you use a key exchange algorithm, this key exchange algorithm, this is a quantum resistance algorithm. Like even the quantum computers cannot break this key exchange. So we can use for our autonomous vehicles, okay, for our purpose. So thank you, everyone. With this, I'm concluding my talk. Any doubts you have, you can ask me now. Thank you, everyone, for patiently listening. If you have any doubts, you can ask me now. Any doubts?
Dear participants, sir is allotted for question and answer sessions. If you are having any queries regarding in this particular session, kindly you can raise the doubt. Vikram sir is ready to give the proper solution for your question.
Oh, you can ask anything. No need to worry about. See, you can ask any general question also. Okay. And by the way, let me give you, I can give you like fancy slides and everything. Nowadays, you know that getting from ChatGPT or some AI tool is easy, but why I'm not giving you is very, very fancy or colorful. I want to show you what actually I'm working. I don't want to give which I'm not working to this, okay? That's why we went like somewhat into the details of the algorithm. So from faculty side, I can ask any questions like, hello sir, can I end the session or any
Sir,
questions?
Mama, kindly check.
Hello, sir.
Yes, sir.
Hello.
Yes, sir. Yes, sir. Yes, sir. Yes, sir.
So,
Yes, sir.
regarding
Sir,
AE's autonomous underwater vehicles, we use a method called dead reckoning mechanism.
Mm.
But during the schema exploration, so when it is connected through optical link, the secure communication is not happening through that method. Is there any reason to? Is there any reason for that?
Actually, I'm not working on this physical, but I'm only working at a hardware implementation side only.
Okay.
Usually, you mean your underwater vehicle is connected to optical cable, sir?
Yes, sir. Yes, sir.
So you have connected wires always, correct?
Yes, sir. It's like a the tethering mechanism that is called tethering mechanism where wires are connected, but the vehicle is it's immersed in the water body to a depth of 10. But when we measure that using that optical links, that jittering rate is very high.
Sir, I think that maybe that model, whatever you are using, that transmission for optical line, that is maybe attenuation is happening, sir, maybe.
Attenuations we have observed for one two models where prototype is also there, but the
Mm.
problem is when we are communicating through the satellite network. So the communication happens through satellite. So satellite through transponder
Oh. Oh, so
that is
okay,
the
okay. Okay, okay. So in that case, what usually these lasers are not, you know that I have told you correct. Usually lasers are good for that surface kind of thing or any
yes,
RF thing. Usually acoustic signals is what usually they use for that underwater vehicle communications.
yes, sir.
That is maybe you can check into that. Actually, I have got option. This one in at NTU, there is a person. She came and she actually surf a driver kind of thing. She went like underwater vehicle 6,000 meters and everything. She explained that time like it. So always
Okay,
she told always either you can connect like a regular cable or you have to use. But I didn't work that hardware side, so that I have very less idea about that. But any
okay,
algorithm implementing what algorithm to choose for the underwater vehicles, I can help you in the software point of view also.
okay, sir.
Mhm. Okay, sir.
sir, sorry, sir. Yes, sir. Sir, thank you for joining with us, sir. We are receiving very good feedback from the participants,
Mhm.
sir. This session
Okay.
is more informative session, sir. Our participants is awaiting for your tomorrow's session also, sir.
Okay, sir. This is actually I'm working.
Yes, sir.
Let's
Yes,
see
sir.
how it
Yes,
is.
sir.
Okay.
Yes, sir. Yes, sir.
Don't,
Sir, we are
thank you, sir.
yes, sir. We are very much thankful for participating at a sponsored 1 week faculty development program, which is organized by Department of Computer Science and Engineering in NBKRIST, sir. Thank you, sir.
Mhm.
Thank you very much, sir.
Thank you, sir. Thank you for inviting me.
Sir,
Thank you,
one
sir.
thing. Sir, Ma Ritika?
Yes, sir.
Yeah, yeah.
Yes, sir.
You can start.
Dr. Vikramkumar, sir, thank you so much for joining the session. I would like to extend my heartful gratitude for sharing the invaluable insights and expertise with us today, sir. Your presence has enriched our understanding, and we also thank you for your enthusiasm and engagement, sir. Thank you, sir.
Sir, thank you, sir, Vikram, sir. Thank you for giving your valuable time for joining our FDP program, sir. Thank you very
So
much,
thank
sir.
you, sir. And okay, thank you very
Thank
much,
you.
sir. Chandrakant,
Thank
sir.
you very
Thank
much,
you.
sir. Thank you, sir.
Okay, sir.
Thank you, sir. Thank you, sir. Dear participants, We will take 5 minutes of break. Next session is going to be start sharply by 7:30. Kartick sir is already joined, who is working as an associate professor in the Department of Computer Science and Engineering from IIIT-SriCity. Dear participants, kindly take 5 minutes of break. By sharply 7:30, the session is going to be start. Dear participants, kindly join the session. The eminent resource person from IIIT-SriCity. Yesterday we received excellent feedback from Dr. Kartick, Sutradhar sir, and sir will be joined for this eighth session. Dear participants, kindly join the session. Sir, very good evening, sir.
Good evening, sir. Good evening.
Sir, very good evening, sir. We are very much happy to see you, sir. Happy to
yes, thank you.
Sir,
I was.
Please, sir, today's session, sir.
Thank you so much.
Sir. Once again, we would like to express our sincere gratitude for joining 2 sessions for our ATAL-sponsored one-week faculty development program, which is sponsored by the IICT ATAL agency, sir. On behalf of the Department of Computer Science and Engineering, we can read it as a more prestigious, and we are conducting this FDP as a more enthusiasm manner, like because of your good personality, sir.
Thank you so much, sir.
Ma Ritika?
Yes, sir.
Yeah, kindly introduce today's our eminent resource person, Dr. Kartick Sutradhar, sir, Department of Computer Science and Engineering from IIIT-SriCity. Sir is very well known for our all participants. Today, yesterday, sir received very excellent feedback. We are also inviting us. We are conducting one more offline session for with sir permission. We are planning to conduct one more session in quantum computing to our students now. Kindly introduce Kartick Sutradhar sir now.
Yes, sir. Good evening, everyone. It's my pleasure to introduce our esteemed resource person for today's session, Dr. Kartick Sutradhar sir, Associate Professor in the Department of Computer Science and Engineering at the Indian Institute of Information Technology, SriCity. Dr. Kartick Sutradhar sir has completed his PhD in Computer Science and Engineering from IIT Dhanbad, MTech in Information Technology from NIT Durgapur, and BE in Information Technology from the University of Burdwan. Sir's research areas include quantum computing and cryptography, and Sir has also published several SCI or SCIE index journals. Dr. Kartick Sutradhar sir has also filed a patent for method and system for secure multi-party quantum aggregation. We are very honored to have Dr. Kartick Sutradhar sir share his expertise with us again today. We welcome you, sir.
Thank you so much. Now we are going to hand over this session for you, sir. Thank you, sir. Thank you for joining.
Thank you so much, sir. This presentation is visible to you, correct?
Yes, sir. Yes, sir. Excellent. Okay. Excellent.
So thing is like that. Today I am going to discuss about the fundamental of quantum circuit and design. Basically, all the quantum circuits are based on the quantum gates. So before going to discuss the quantum circuits and all, we should first know the quantum gates. Okay. So as I earlier said that all the quantum gates are reversible gate. So this is the outline of my presentation. I am going to start going to discuss this quantum gates as well as one of my protocol which I have designed, and there is a circuit realization of that, and then I am going to conclude it. So basically, quantum gates are the fundamental building blocks of quantum circuit. Okay. So as we know that we have a lot of classical circuit, integrated circuits are there, and that gates are based on classical circuits are based on our classical gates. Okay. So we know already one theorem is there that is basically called our Moore's law. That's Moore's law is saying like that each and every 18 months or 2 years in an integrated circuit, transistor will be double. So all the gates are made using by the transistor. So when transistor will be double, then our gates also will increase. So whenever this gate will also increase, our basically in integrated circuit, it will basically produce more heat and all. So whenever it will produce more heat, we will not get our exact output, whatever we are trying to get. Okay, so then this quantum gates came to that picture. These gates are all reversible gates. Reversibility means I can give example of classical gate that is reversible. That is only NOT gate is reversible. So it's like that. If whatever input we are giving, and after that we are getting some output, again that output, if we'll give to input, we'll get the original input whatever we have given. So this is basically called the reversibility. Okay, so and whenever this reversible, so we no need to basically store that inputs. So this reversibility concept will give us one advantage, that is basically we no need to store the information, as well as we can reuse these quantum gates. So here basically there is quantum 3 type of quantum gates are there. One is 1 qubit gate, second one is 2 qubit, and then 3 qubits gates are there. So here I'm going to discuss one gate that is basically called NOT gate or Pauli X gate. So it is basically whatever input we are giving, it is giving us that output. So it's a look like. So it's look like, suppose there is a X gate. So if we are giving their input as a 0, we'll get output as a 1, or if we are giving it as a 1, then it will basically produce a 0. So this is the basically concept of this quantum Pauli X gate. Okay, so what is the representation of this gate? So last class I already discussed one notation that is basically called Dirac notation. DRIC, whatever. It's basically called Dirac notation. I forgot that spelling. Okay, so this Dirac notation is like that. RSC or something like that. Okay, so whatever. So if it representation is like that, if 0, we will represent this 0 as in the matrix form of 1 and 0, and this 1, basically these are the Kate function. Last class I already discussed. So zeros and 1. So this is basically the representation of the zeros and 1. So this gates, how we can represent, basically this is a representation of X gate. We can represent it like that. Whatever input we are giving and whatever output we are giving, if it will, and this is basically called gate notation. Gate notation, and one more is that which is basically called bra. So bra is just opposite of that. It is basically 0, and we will represent it as, this is basically column matrix, this will be row matrix. Okay, so it will be 0 and 1 like that, and this will be the 1 will represent as a 0 and 1. So this is basically representation of this Dirac notation that is called bra, and called 0 will represent as cat 0 will represent as a 1 0 as a column matrix, and this bra will represent as a row matrix. Okay, so if we'll see this this X gate basically. So whatever input we are giving 0, we are getting output of 1. So get 0 we are represented as a 1 0, and 1 we are represented as a 0 1. Similar to that, this 1 we are represented as a 0 1, and 1 we are 0 we are represented as a 1 0. So if we'll multiply it, we'll get 0 1 0 0, and this is basically our called matrix multiplication. So if we'll multiply it, so we will get it this form, and we will get this 2 cross 2 1 matrix will get. So this is basically representation of the X gate, or this is basically called quantum NOT gate. So if you see that there is so many gates, Pauli gates are there, Pauli X gate, Y gate and Z gate. 3 gates are there. That is, I have taken only one gate to show the example of this single qubit gate. Then this is basically implementation of this X gate. So I have implemented this gate using this QSkit. I have used a platform of Google Colab. So here what I did, I have taken the package quantum circuit, and this is basically 1 qubit gate. That's why I have taken 1 qubit, and this is basically X gate quantum circuit. X gate, we will represent it like X, okay, and we are considering there is only one input, and we are drawing it. So we draw. So there is our state vectors. So what I have given here, input we have given 1, okay. So 1 means our output will be 0. Whenever I'm giving input here as 1, it will give output as a 0. So what is the 0 representation of 0? So as we know that representation of this get 0 is basically our 1 0, okay. So we are getting the same thing here. You can see that in first our vector form we are getting 1, and this vector we are getting as a 0. So this is basically one implementation of this Pauli gate. So next is basically our Hadamard gate. This is very well known gate. So if we are giving input of this Hadamard gate, then output we will get as in this form. If we are giving input as a 1, then we are getting its output form. So similar to that, our previous gate, if we will do the calculations and all, and we will get this matrix form. So this is basically this is also one more our single qubit gate. Then coming to the 2 qubit gate, this is basically a very interesting gate, which are well known. Hadamard and this CNOT gate can create the entanglement. So this is basically 2 qubit 1 gate. So if we see this 2 qubit gate and all representation, how we have done. So this is basically one CNOT gate, how we are representing it. It's basically, if we are giving as their A and their B, if we are giving it, then we will get as exactly A same, and here we will get it B XOR A, we will get it, okay. So this is basically representation of, so this first one we are calling is control qubit, and second one is calling as a target qubit. So what is the truth table of this one? We'll see. If we perform the calculation also, we will get it. So if we are giving there 0 0 as the input, so 0 is our control qubit, target qubit also our 0, so nothing will change here. We'll get 0 0 exactly. And if we are giving 0 1, so same thing. If we'll see this perform this calculation, we'll get there nothing will change, 0 1 will get. So whenever we will come to this 1 and 0, so if we perform this XOR operation, we will get it is 1 1, and next one whenever we will give 1 1, we will get 1 0. So here you can see that one thing, whenever our control qubits are 1, then this bits are flipped. Here you can see that. So whatever 1 is there, then this is 0, it's become 1, and whenever this is 1, it's become 0. So its logic is like that. If our control qubit is 0, then nothing will change. It will be like, it will not be flipped, it will be like as it is. But if our control qubits are 0 1, then this our target qubit is going to flip. So same thing is happening in this our CNOT gate. And one more thing is that why we are calling its reversibility. Check it once. 0 0 is input, we are getting 0 0 output. 0 1 input, we are getting is 0 1 output. 1 0 we are giving, then 1 1 we are getting. Whenever we are giving 1 1 again as an input, we are getting 1 0 as a output. So here you can see that input was 1 0, getting output as a 1 1. Again that input we are giving as a 1 1 and we are getting 1 0. So here this is basically we are coming to again that initial our inputs. So this is basically called the reversibility. Okay, so if you see that all the quantum gates, all our quantum gates are reversible gate. So this is the advantage of our quantum gate over our classical gates. So these are the basic mathematics of our CNOT gate. So this is basically CNOT gate matrix. How we are getting this matrix, we'll see that. Okay, so there one new thing will come to that picture, that is basically called tensor product. Okay, so what we was getting as input, so this one we can say it like that, summation of or we can say it like that.
Sir, sorry for interrupt. Excuse me, sir. Sir, is it K-map, sir?
Which one? K-map?
Is matrix representation like K-map representation, sir?
No. This is matrix. No. This is matrix representation of quantum gates.
Oh, sorry, sir. It looked like min terms and max terms in K-maps. That's why I'm asking.
No. It's not like that. Okay.
Okay, sir. Thank you.
So it is basically summation of whatever our input put I, and it is basically get function of output put our I. Okay, so what will happen there, we'll see. So we have given as a 0 0, sorry, so if we are giving as a 0 0, output we are getting as a 0 0. Okay, then plus, because it is a summation of that. Then if we are giving as a 0 1, then we are getting as 0 1. Then again, because we will get the 4, because it has a 4 input. So if we are giving as a 1 0, we will get is a 1 1, plus if we are giving as a 1 1, we are getting as a 1 0. Okay, sorry for that. So here we can see that this is basically called 1 0. Okay, so how we are representing this 0 0, this is basically right now in superposition state. What we can write it like that, 0 we can divide it like here. If we write it 0 gate, this is basically called tensor product. 0 0, we can write it like that. So similar to that, our 0 and tensor product of 0 0, we can write it like that. So if 0, already we know that what is the matrix representation of 0. 0 is basically 1 0, tensor product 1 0. Then if we see that this is basically column row matrix, it will be 1 0 and it will be 1 0. If we'll multiply it, tensor product, how we'll multiply it, it will come one column matrix 1 we'll multiply with 1. 1 multiply with 0, we'll get 0. Then 0 multiply with 1, we'll get 0. Then 0 multiply with 0, we'll get 0. Then similar to this one also, if we are multiplying it, so we are getting this matrix, column matrix, then it will automatically will get row matrix. If we'll multiply it, we'll get 1 4 cross 4 matrix. So what will be that? 1 multiply to 1, then all will get 0, then 0, all will get zeros. So this is only we got for only one input. So this only for this one. Then we will get for this one more matrix, for this one more matrix, this one more matrix. So whenever we will total we will add this all four matrix, we will get this one matrix. So next one here, what we are going to get, we'll see. So next one, this is one matrix we got. The next matrix we are going to get here like that. Next matrix we are going to like 4 cross 0, this one 0 0 0 0 0 1 0 0 0 0 0 0. This is for our second one. For third one we will get this plus only 1, and then fourth one we will get this one. If we add all those matrices, then we will get this one matrix. This is basically matrix representation of quantum bit, matrix representation of CNOT gate. So whatever CNOT gate we are seeing, behind that this matrix is there, this mathematics is there, and this tensor product, we know that this tensor product, dot product, then scalar product, all those things. So this was basically our CNOT gate matrix representation of that. We'll see that implementation of that. So I have implemented this one using that Google Colab, using this QSkit. So here you can see that I have used their quantum circuits package. Then I have taken this CX, basically representation of the CNOT gate. Basically C is basically control and X is NOT gate. Previously you can see that I have only used that X gate. So this is a 2 qubit gate, and we have 2 qubits, zeros and 1, and we have to give that our scanning, or which one we will give that indexing. We are basically doing that is zeros and 1. Okay, so here you can see that I have taken one example. Okay, I am giving here input. So how this input is there scanning? Input is scanning from right side to left side. So Q0 is 1 and Q1 is 0 here. Okay. Then this is a state vector like previous one. So if we'll see that our input as a 1 0 input, we have given this one, so we'll get 1 1. Okay, so what is the representation of this 1 1 gate? 1 0 1 1 1 gate. So 1 1 will basically our if we'll write it like that, 1 1, that is basically our tensor product. 1 1 will get 0 1, and we'll get 0 1. If we multiply it, all bit will get 0 0, last bit will get 1. Okay, so here you can see that this is all bits are 0, last bit is 1. Okay, so this is basically implementation of the CNOT gate. So similar to that, we have seen this CNOT gate. Next we'll see that show up gate. how this Schwab gate is working. So this is basically Schwab gate. So Schwab gate truth table is like that. Whatever input we will get, it will get the give the output as the opposite one. So what we have used here, we have used that C0 gate, and we have used same C0 gate with the index change. So here you can see that truth table of the C0 gate 0 0 we are giving. It is basically swapping 0 0 as that. So if 0 1 we are giving, it is swapping as a 1 0. Whenever we are giving 1 0, it is swapping as a 0 1. And whenever we are giving 1 1, it is basically giving us 1 1 as a output. So here you can see that one thing 0 0, there we are getting 0 0, no problem for that. Whenever we are giving 0 1, it is giving us a output as a 0 1 1 0. Again that 1 0, when we are giving to this input 1 0, we are getting again 0 1. So here you can see that whatever input we have given initially, after that one round we are getting the same input as the output. So this is called the reversibility. Each and every gate I am showing that all the quantum gates are reversible. So this is basically matrix representation of this Schwab gate. Already I showed one gate quantum C0 gate. So similar to that you can calculate it. So you will get that values of this one. Then come to this implementation of this gate. So I have implemented this one. So there is a 3 C0 gate I have taken. Only second C0 gate you can say that I have changed the indexed. So this is right now as a control qubit, this is as a target qubit. So whenever I have taken it, then it's look like that. So this plot, all those things you can do there only itself, and there I have given as a 1 0 as the input. So 1 0, it will give us the output as 0 and 1 it will give. So 0 1 representation of this column form, column matrix form will get like that 0 0 1 0. Then come to that Toffoli gate or CC NOT gate. Okay, this is basically this 3 qubit gate. So it has a 2 control qubit, A and B, both are the control qubit, and C is basically our target qubit. So this is basically our output of that. So whatever we will give as an input, exactly same thing will give as output of control 2 qubits, but last one will be perform that XOR operation. Okay. So this is basically truth table of this our 3 qubit gates. So if we are giving 0 0, we are getting 0 zeros. 1 1 we are 0 1 1 we are getting as a 0 1 1. So here you can observe one thing. Whenever our both the control qubit A and B basically are the control qubit. So when both the control qubit are 1, then only this target qubit flipped. So this 1 is there, this 1 will be flipped, 0 is there, that 0 will be flipped here. See that? And when both the control qubit are 1, okay, then only this bit will be flipped. So here you can see that it becomes 0. So here you can also observe the reversibility. So whenever we are giving as a 1 1 0 as an input, we are getting triple 1. Whenever we are giving triple 1, we are getting again that 1 1 0. So this is again, it's proving that this is a reversible gate. So this is basically matrix representation of our CC NOT gate. Okay. So it's a very huge because of 2 power 3 means 8 cross 8 matrix is there. So this is basically matrix representation. I have implemented this one using these Q skits and all. So you can see here that 1 1 0 we have given. So it output will give as a triple 1. So triple ones, if we'll see that matrix representation, we will get it like that. I'm showing it on. So what is the matrix representation of the triple 1? So here triple 1 means 1 1 1. If it is in cat form, then we will get it like 0 1 0 1 and 0 1. If we'll multiply it, 0 with 0 we'll get 0, 0 with 1 0, 1 with 0 0, 1 1 1. Basically this is a tensor product, and then 0, 1 is there. Again, if we multiply it, we'll get 0, 0, 0, 0, 0, 0, 1. So this is basically the matrix multiplication of this our gates. So this is basically our gates. You can see this one. So here you can see that after getting all zeros, we are getting this one. So this is basically for 3 qubits gate matrix representation. Okay, so I have proposed one protocol that is basically called secure multi-party quantum summation protocol. Okay, so this circuit I have designed. It is published in IEEE Transaction on Circuit and System. So this is I have published during my PhD. So here I have used some X gate. X gate is nothing but our quantum X gate, and Hadamard gate, quantum Fourier transform here we have used. Okay, so that there is not that much detail is given there. This is basically one circuit diagram because it's a multi-party computation. So it's like use number of players should be there. Okay, or many gates should be there. So because of that only we have only given the overview of this circuit diagram here. So first I'm going to discuss this what is secure multi-party computation. Okay, so it's a very good mechanism for distributed computing. So as we know that we have 3 types of security mechanism. One is cryptography, one more is our steganography, then is our secure multi-party computation. Like secure computation, how we'll compute anything in securely. So first thing is like that cryptography, already everyone knows that things. It is basically secret writing. Steganography means cover writing. Then distributed computing, how we will do in securely. Okay, so why this picture came to, this distributed security came to that picture. Okay, so if we keep everything in our same place and all, okay, it is only depend on one particular machine. So what will happen? There can be a possibility to destroy that particular system, so that it will not be that much secure, or if someone can interrupt that particular system, then that data can be destroyed. So because of that only this our the secure multi-party quantum computation came to that picture. Okay, so I'll see that what is the motivation behind that. Before going to that, I'm going to show you whatever circuit I have designed. Okay, previously I have discussed where I have designed. So this is basically Google Color. You can see that. So if you will design, first you have to install that QSkit. If you install it, so if you will write some code for that, here you can see that I have imported that one, a quantum circuit. Okay, so you can also do similarly, and there you can design your gates as per your requirement. You can give, and it will give you some outputs and all. So it will be better if you are in initial stage of this quantum computing. Your basic things will be clear from here only. So you can go through this, and whatever the matrix I have showed, how these matrix are coming, all those things are you can implement here. Okay, so this is still I think CC not out of legate I kept. So you people also can implement it using this QSkit and Google Colab. Okay. Okay, fine. Then next I'm going to discuss this secure multi-party computation. Why it's need to came to that picture. Okay, so suppose first motivation I am giving to you one thing like that. Yesterday I discussed one thing that is basically called millionaires problem. If two millionaires are there, that is basically A and B, two millionaires. They have some their values, monies, and whatever is there. So they are saying like that I will not disclose, we will not disclose our values and all, whatever values are there, we'll share it with some people or some computers or someone. Then you compare our values. So this is basically called that millennials problem. So this millennials problem can be solved by using this our multi-party computation. So how it can be solved, that I'll say later on. And one more motivation is like that, our satellite. Okay, so our satellite, we know that all are in our orbit only. Okay, so this is basically one orbit and satellite is there. So suppose India sent one satellite to this orbit, okay, and one more satellite sent by Japan, okay, this there, okay. Beside that, okay, so it's basically, you can see here is two common point. Okay, there can be our satellite collide. Okay, in 2007 one Japanese one satellite collide with one US satellite. Okay, so why this satellite collide together? They don't know each other geometric location. Okay, so India sending their satellites in one geometric location and it is speed is different, and some other countries also sending. Right now in 21 lakhs objects are there in universe. Okay, so how this object will not cloud, how we can ensure it, and it's very, there is very sensitive information will be there, like in total country's security system will be there. Basically we are mostly communicating with the satellite communication and all. So suppose if it is public to everyone also, like Indian geometric ocean, China, Pakistan can launch their satellite. Okay, our Pakistan can't, but China can launch their own satellite and all, and they can destroy our satellite if they knows our geometric location and all. Okay, so a few years back we listened some news about that, some satellites sent by some other countries and destroy that things and all. So how can we prevent such kind of incident? Okay, so for that this kind of mechanism can be there. Okay, like we have our United Nations. Okay, so there is maybe 10 nations are there, or 5 nations or 7 nations are there. Okay, so this geometric location we can share with these 10 nations. Okay, not only one particular nations. Suppose we are giving to America, we don't US what is their policy, and they will disclose to some other countries. They can do it. Okay, if some other countries we are not trusted, like Pakistan or other countries is like that only. Okay, so they can disprove it. So what we can do, we can give our satellite geometric locations share only, not only exact value, means exact geometric location. So like that only. So suppose India has a one geometric location like A. Okay, so this A will be shared with country 1, country 2, country 3, like that, country N. Okay, so other countries are there, they have also some values, they will also share with them, no problem for that. So if this A will share with them, only share will give to them. Okay, that sharing mechanism is also there, that is basically called Tipler's Shamir secret sharing mechanism. Okay, so what we can do, we can share the geometric location of our secret, means geometric location, and give to these countries. So suppose out of these n countries, n minus 3 countries, so T is basically one threshold, so their minimum this number of parties should be trusted. Okay, suppose 10 countries are there, we are saying that okay, 5 countries are corrupted, 5 will not be participant there. So they will participate and they can reconstruct our satellite geometric location. Okay, so then what will happen, then next whenever other countries are going to send from this United Nations and all, they will get to know, okay, this is the geometric location of that countries and all. Okay, or share of that, we should not send our satellite in these areas. At least areas will send, you don't send in these areas. So that can be one possibilities. So that is the rough idea of that. Okay, so I have not got much paper on this particular area because very few less incident happen because of that only. But in this millionaires problem is very useful for that. So what is basically this multi-party computation? We'll see that things and all, and with that we'll see try to understand that our Shamir secret sharing. So suppose we have a two secrets of two person, okay, then they want to do the summation of their secret. So suppose there is a person, okay, secret is basically 2, and our B person secret is 3, okay, and there we can consider as a prime is 7, and n means total number of, I given one example, total number of countries, okay. So here it can be computer, it can be some players. In terms of that we can consider it. So suppose there is a n players, n means we can consider here as a suppose 5 we can consider it here. So here we can see that 5, okay. Then we can say that T is minimum T number of countries should be trusted or should be honest. So we are considering as a 3, okay. Here out of 2 we are considering as a corrupted, or they will not work peacefully. And which are the countries? That 3 countries, so we are calling that qualified subset. Their player name I am giving as a P1, that can be country 1 or computer 1 and P3. These 3 are our basically our this computation will perform. So what we are going to do, we are going to do perform the addition of this A and B, okay, that will be securely, so their result will get as a 5, but it will do in the form of distributed computing. So we'll see that how it will, how it is going to do. So what will happen there? Here this A and B is there, so there will be one dealer. The dealer, what it will do, it will share these 2 secrets. So how it will be shared to other players? So it will basically in the form of polynomial. So suppose this is a f of x, this 2 they will take as a secret, so this is basically called a naught. So it's 2 plus, then one random number will be there. Oh, I'm taking random number as a 1 for every one, then x, then x square, and there also can be one random number, okay, as a coefficient. So why this is 1 is a square, this degree of the polynomial should be t minus 1. So t is here our 3, so t minus 1 will be 2, okay. So it will be a square. Then one more for b, g of x, it will be 3 plus x square. So for this simplicity of this calculation, I am taking this polynomial, and everything will be mod of 7, okay. For the simplicity, I am taking coefficient as a 1, so that it will be easier to us to compute, okay. Then what will happen? This secret secret will be shared with all the players P1, P2, P3, P4, P5, okay. So here you can see that total number of players was 5. So 1 to 5 we have taken. So what we'll do right now, whenever we'll calculate the share of the P1, okay, so this is basically calculating by the dealer, okay, and it will share to P1. So whenever it will calculate for P1, so it will, x will be replaced with that 1, okay. So it will be, first one will be 2 plus 1 plus 1, so it will be basically 4. Then our next one will be 1, then will be 0, 1, 4. Then for second polynomial 5, then 2, 1, 2, 5, okay. And this each and every player, they don't know each other's shares values. So suppose this is one country, this is one more country, this is one more countries, or they are in different places, geometric locations are different there, okay. So they don't know each other shares and all. This P1 only knows 4 and 5, okay, like that only. So what is here we are getting, then what they will do, we are basically performing the summation. So they will add these two shares. So whenever we will do add these two share, 9 will get 9 mod 7. If we'll do, we will get 2. And here we will get as a 3. Then we will get as a 1. Then we will get as a 3. Again we will get as a 2. So these are the shares right now, each and every players is there. Okay. Then what they will do, this player P1, P2 and P3, they will calculate the Lagrange interpolation. Okay. So in some, basically Shamir secret sharing, it has a two phases. One is secret sharing. So that already we have done, each and every secret we have shared. And one more is that reconstruction. That reconstruction will be done by, suppose we have taken 3 players here, P1, P2 and P3. They will perform the reconstruction. So this reconstruction, whichever the parties will do, they will calculate that Lagrange, perform the Lagrange interpolation. So here Lagrange interpolation, we are considering these values as a lambda. So how they will compute, for player P1, it will consider 2 and 1 minus 2 multiply of 3, 1 minus 3. So it will get as a 3. So if lambda 2 will calculate, we'll get as a 1, 2 minus 1 multiply of 3 and 3. Basically this will be our this will be our 2 minus 3. This will be our 2 minus 3. If we calculate it, we will get is minus 3. If we perform the mod operation of this minus 3, we will get as 6. 6 not, we will get as a 4. Because 3 mod will get as 4. So 4 we are getting. Similar to that, lambda 3 will be calculated, and this will be basically our 2 and 3 minus 2 multiply of 1 and 3 minus 1. So it will be basically 1. So right now we got here 3, 4 and 1. So what is the formula of that? Calculate this A and B. A plus B will be multiply of these shares. Okay. So 2 will be multiply with that first player Lagrange value or lambda 1. So 2 is multiply with 3 plus 3 will be multiply with minus 3 not. This is a 4 now. So now we can consider as a 4 plus 1 multiply with 1. Okay. So what we'll get here 6 plus 12 plus 1. So here we'll get it 19 mod of 7. Then what we'll get as a 5. So here you can see that our secret was 1, 2 and another one was 3. So this 2, if we do addition, we'll get 5. So here after computing this one, we got exactly the 5 as our secret. So this is basically called distributed computing. So this secure distributed computing. So here you can see that each and every players are in different places, and A also not shared his value, means exact value. He only shared the share values. B also shared the only the share values. So here you can see that if this only one player will not get to know what is the value of B, so they collaboratively can calculate that particular values and all. So this is basically called the secure multi-party computation. So here we have performed that secure multi-party summation. So this was the concept behind this secure multi-party computation. So same thing we have did in this protocol, in the manner of quantum. We have used some quantum entanglement, quantum mechanics, C0 gate, and then we have built this circuit using this previous all those gates and all. So if your basic things will be more clear to you, then you can build these circuits and all. Okay, and then this circuits, this symbol, you can see that this is basically measurement operation. Okay, so measurement, as you know that in quantum computing, if we are measuring some particular state and all, we are getting some information in the form of classical. Okay, so this is basically that about the circuits and all. So here I'm going to conclude it. Okay, so all the quantum gates are reversible. Already I showed that, because due to that only we required less number of gates and all, and we can, when less number of gates will be there, there's less number of transistors also will be there. It will not be produced that much heat and all, so we'll get that our accurate result in terms of these things. So these are the basic fundamental things of these quantum circuits, and I have given one example of secure multiparty quantum summation. So I think it's useful for this quantum circuit set design. Okay. So these are two. I think one book is there and one reference is there for some secret sharing. It's basically how to share a secret. So I already showed that example of this secret sharing and all. And this is one book, Quantum Computation and Quantum Information. It is from Nilesh and Chang. Both are, I think Chang, he is in MIT. Okay, so you can refer this book. It is online available. It's a very useful book for quantum, for learning this quantum computation. And some our Indian good lectures are also there. One is NPTEL, that is basically Deepan Ghosh is from IIT Bombay. You will get that NPTEL lecture. This basics, all whatever in fundamentals of quantum computing are there. We taught already. So this was from my side. Okay, if you want to know any questions from these quantum gates, quantum circuits, how I designed all those things and how I implemented. Basically, I have not designed, but I implemented these things using this one. So if you have any question, you can ask me. I'll feel free to give the answers. So these are the things from my side. And this kind of lectures will be more useful if we will physically present on board. If we present, we have so many limitations here. Properly, I am unable to write on board. So that is one thing, and all the things are there behind so many mathematics. Okay. So if we can understand that mathematics and all, then we can do the fundamental research also. Okay. Basically, this our National Quantum Mission recently launched. Okay, so they are basically looking for the fundamental research of quantum computing. So these things only they are looking for. So if we know these basic things of quantum computing, then we can design the quantum algorithms also. So it's not the right time to jump directly to that application. If you can do some fundamental research, then it will be very good for us. If you can design few more basic protocols or basic we can design some more useful gates and all, then it will be very useful for us. Okay. So these are the basic things. If you will go through this, then you will get more ideas, and you can design some good circuit. So if you have any question, you can ask me. Okay, if you require some more explanations of this matrix representation of these quantum gates. So there is so many gates are there. I am because of these limitations, all those things, I am not unable to discuss all those things here. Okay, so if you want to really know, you can ask that things and all. I will give my whatever I knows. I'll try to deliver to you. So if you have question, you can ask regarding this quantum circuits, all those things. How to design. So C not gate is clear to you, correct? So C not gate is basically 2-qubit gate. Okay. So C not gate, if we get give input as a 1 0, so output what we'll get? Can you show anyone? Can you say anyone? In chat box you can write. If we'll give 0 as an input, 1 0 as an input, then what we'll get as output? No, basically 2 inputs get, that is na. So we'll get 2 output also. So it's not only 1. So we'll get something else. 1 0 if we'll give as an input, then we'll get output as a 1 1. Correct. So this was from my side. If you want to ask any questions, okay, again I'm asking, so you can ask some questions from there, and later on I may conduct one more session in the institute by going physically. Okay, so those people are available, you may also join there. How to observe that this behind that multi-party secure communication. Multi-party, there is no secure communication. It is basically called computation. Okay, so this is okay, fine. Basically, I have not explored that one, so okay, I need to little bit explore this one. Then only I can say that exactly. So you have asked one question that is very good question. It's like that, how to decide which gate will be used where? Okay. So this is one very good fundamental question. Okay. So see that when you are creating that entanglement, correct? So entanglement is the fundamental things. Entanglement you can create by using our Hadamard gate as well as our CNOT gate. Okay, so when you require to create some entanglement, so you can use this our Hadamard gate as well as our this CNOT gate with Bell state also. Okay, means it will give as the form of Bell state. Okay. Okay, a Fratkin gate I already designed. Okay, so what I'll do, because of this limitations I have not kept it here. I will give you, I will send to sir. Okay, and you collect it from sir. Okay, so similar things only Fratkin. I have designed that one. If it's possible, I'll show to you. Okay, I think my window is visible to you people, correct? So here, if you'll go, one paper I am giving to you. Okay, that is basically called matrix. Matrix representation of this quantum gates. If you go this paper, okay, this paper is not that much useful. So many incorrect informations are there, like calculations are there. So whatever I taught here, so here some wrong calculations also given. Okay, so what you can do, you can see that Fratkin gate, this logic is totally wrong. Both the logic you can see the same. Okay, so one will be C will be dash and B will be 1 dash. Okay, so this is basically, this is Atkin gate, but if you go through this logic and all, you will get this output. If you go to implementation, you will get on matrix. Maybe this matrix is wrong, okay, but similar way you can implement it, okay. So this is basically Fatking. So here will be logics and all. I'll share with sir. Okay, I have already implemented. I'll share with sir. You just collect from sir. Okay, Fatking gate, PR gates, all those gates are there. Okay. And one more thing is saying that, sir, can quantum protocol be simulated classically? Basically, classically, you can't write the logic. Okay. So if you write the logic, you will get the output. But if you are doing the coding using this QSkit and all, so you will get to know what are the operations are going to be used and how this. If your basic things are clear, then automatically you will get to know that automatically you will get to know that your result and all. Okay. So it will be better if you are going to, basically everything is classical till now. Okay. So quantum we don't have much. So you can do one thing, you can simulate it, or you can write the code on Google Colab or Penny Lane came. So you can write their codes and all. Okay. So how to decide which gate fit to a problem at hand? So think is like that. Suppose you are designing one protocol. Okay. So if you are trying to do the secure communication. So secure communication means you need to send some information from one place to another place. That is basically called the teleportation. So whenever we are doing the teleportation, if we will entangle the qubits to send to receiver side, then what will happen there? Their receiver will get to know if there are any bits altered or not. Okay, if we are sending this classic our entangled state and all. So in this case, this our attacker detection is possible. Okay, so such kind of things, when you require such kind of entanglement and sending some information and all, you can use our entanglement and all. Okay, so how to design circuits while decoherence error rate is present in single qubit and multi-qubit system. Okay. So thing is like that, I never thought it like that. Okay. So if there is any error rate is there, okay. So I need to check it once. Okay. So then only I can give you that proper solution. So I am noting your this comment. Okay. So it's very useful comment for me. So I am taking your comments. Okay. It's very useful. So how we check time complexity in between the classical and quantum computing? See, the time complexity, it is in different way you can calculate the time complexity. Some people are calculating this time complexity in terms of seconds and all. Some people are calculating in terms of their in terms of means computation. Okay, so it is depend on the different protocols and all. But in classically we are sometimes we are calculating it is in terms of our order, sometimes it's in terms of our basically in terms of time, seconds and all. Okay, but in quantum computing, what we are doing, we are taking that, basically considering two type of complexity there. One is communication complexity and another one is computation complexity. So in terms of that thing, that you can check it once. Is there any specific tool for checking the time complexity? Is not there, but mathematically you can prove your time complexity. There is no such algorithm tools for checking that complexity. So what will be the performance metrics we need to consider? So performance metrics you can consider in terms of computation cost as well as the communication cost. Communication cost, how you can decide that things like how much meshes particle and decoy particle you are sending for this communication. So that can be one type of your metrics to compare in terms of communication. And if you are talking about computation cost, then there some operations will be there whenever you will performing any algorithms, like how many types multiplication you have used. How multiplication is very complex, and it is complexities are there. So basically in multi-party computation, when we are considering in terms of how many multiplication we have used, then how many gates we have used. So gate has its own complexities and all, like such kind of things are there. And then you are talking about algorithm. No such algorithm is there, okay, for that checking the complexities and all. Sir, why quantum bit commitment is considered to be insecure? Um, there can be various reasons for it. Okay, so suppose we are sending some quantum bits uh, without you know first of all without proper secure channel. That can be one things can be authentication problem, and there can be intercepting problem. There can be entanglement measure problem, means entanglement problem. So sometime we are sending some information and all without doing entanglement and all. Okay, so entanglement only one things, it will give us security, as well as it will tell us to our it will basically tell us to our any attack is there or not. Okay, so such kind of things are there. So it's not like that only exactly one answer is there for that. Okay, there can be various reasons. So there one problem recently there one that is basically invisible photon attack as well as delay photon attack came to that picture. Okay, for this is basically by using some softwares and all, or some viruses and all, basically trying to trying to delay the for our photons and all, and try to make it invisible like that. So such kind of things are there. Okay, noise decoherence unmeasured. Yes, I'm not getting that things whatever your question is there. Yes, decoherence unmeasured issues. That is one problem. Okay, but we have to find out the solution for it. Okay, so one thing is there in quantum communication, major thing is noise. Okay, there is a problem with this noise coherence. If any other questions are related to quantum computing, quantum circuits and all.
Yes, sir. Last 15 minutes were assigned for question and answer sessions, dear participants. Sir, thank you for giving your valuable time specifically
Thank you
for,
so much, sir.
yes, sir, specifically for question and answer session, sir. We are very much grateful for contributing your valuable deliverables without any restrictions. You are accepting our request on behalf of the Department of Computer Science and Engineering and NBKR-IST for the ATAL sponsored faculty development program on quantum cryptography enabled autonomous underwater vehicles. Thank you, sir. Thank you very much, sir, for your great
Thank you so much. Thank you
participation
so
and
much,
your
sir.
valuable deliverables, sir. We are receiving
And thank you
very
so
well
much.
feedback from yesterday's session and today's session.
Thank you,
Sir, for your respected session, sir. Yes, sir. Thank you very much. We hope we are planning to arrange one more offline session in our NBKR Institute of Science and Technology without any violations. You can kindly accept our request from the Department of
sir.
Computer
Yes,
Science and
sir.
Engineering, NBKR IST, sir.
We'll decide one time and we'll go physically. I want to give physical talk there rather than this online talk. There is so many limitations are there. I can't express that things whatever I want to deliver. Okay, and there will be so many lot of critical questions and all. So I want to face that things and I want to learn also from there. I got one very good question today. Okay, so I have to study for that and I will try to get solution of that. Many questions I got. Okay, that is touching. Okay, to me. And thanks a lot. Those people are asking such questions. I always appreciate the questions and all. Okay, and this from these questions is making me hunger to learn this quantum computing.
Yes, sir. Yes, sir. Yes, sir. Sir, once again, we are very much thankful to you, sir. Ritika?
Yes, sir.
Yeah. Our Kartick sir will be there, ma.
Yes, sir. Dr. Kartick Sutradhar, sir, thank you so much. I would like to extend my sincere gratitude for sharing this expertise on the fundamentals of quantum circuits and design, sir. Your insights have been enlightening and have added significant value to our understanding of this cutting-edge field, sir. I also thank the organizer of the ATAL Online FDP for facilitating this informative session today. Thank you all the participants for your engagement. Once again, thank you, sir, for your valuable time and contribution.
Thank you so much for giving me this opportunity, and thank you everyone. It was a very nice interaction with you people, and in future I want more collaboration. Even if you people want to work in this domain of quantum, I think all of you are interested. So it will be very good if we can create one good group and we can do some good research and we can contribute towards our nation. That is basically our national quantum mission. That should be our target. We want to see our countries in topmost in terms of quantum computations and all. And government is spending so much money for that. I think we have to utilize it, try to get some project from there, and try to implement some of our own protocols, own algorithms, and all. Then it will be very good for us. And I think we have to grab this opportunity to everyone. Those people are we are in academia, we are in industry, and all. So if we will come together and we will do something for our nation, so it will be very useful for our next generations. At least we are the first generation we are doing research in this quantum. Okay, so maybe our next generation will be more advanced and our government will be more focused on this quantum. And fortunate one things we got in one quantum hub in Amravati. Okay, that is in Andhra Pradesh. So we are very fortunate for that. So we can utilize that, our resources. So last time I talked with their one secretary, he was the National Quantum Mission Director, and we did one workshop there also. They offered us to utilize that quantum values, quantum computer for our project and all. So we should grab this opportunity and we should work together and do something better for our country.
Thank you, sir. Thank you very much, sir.
Thank you so much. Okay, sir.
Haribol, sir. Thank you.
Okay, William sir. Okay, sir. Okay, sir.
Thank you, sir. Dear participants, today's session is wonderful session by the expert resource person, Dr. Kartick Sutradhar, sir. Now we are going to leaving the session. By tomorrow, we can join the session. Thank you one and all. Session 7 feedback. Thank you, sir. Thank you one and all.